What's up, everybody? I'm Steve, and this is USACO 2024 December at the bronze level. Problem number 2, Farmer John's cheese block. Farmer John has a block of cheese in the shape of a cube. It lies on a three-dimensional coordinate plane extending from 0, 0, 0 to n, n, n. This is important to note. The size of the cheese block, the size of the world that we're working in, starts in 0, 0, 0 and extends in terms of three coordinates. 1, 2, and 3, making a cube of cheese that has n on each side, where n is between 2 and 1,000. Now, this is a big red flag. 1,000 times 1,000 times 1,000 means you're not making a Boolean array with this. I went ahead and tested it just for giggles. Code that just initializes a 1,000 by 1,000 by 1,000 Boolean array is already too slow and times out on the first test case. Right off the bat, we know that we are not going to be able to brute force this. Your x coordinate is heading to the left side here. Your y coordinate is your vertical, and your z is like this. I rotated this slightly because I didn't like the diagonal view. I went ahead and made x like this, my y be my vertical, and then my z I rotated so that's like a front face. To me, having a front face was a little easier than having it diagonal. So then I have xy is my left side face. I have yz is my front side face. And I'm going to kind of keep that perspective while we're describing this. That way I can kind of have left, right, backward, and forward, and then up and down as my directions. Farmer John will perform a series of Q update operations on the cheese block, where Q is between 1 and 2 times 10 to the 5th. Here's another big red flag. We can't look at every cut against every cut because Q 10 to the 5th is going to be too much for an n squared solution. They're really cranking us down on this one. This is almost like a silver problem. Because of the level of time complexity, we can't simulate this. We can't brute force this. We can't compare all of our operations to all of our other operations. And not only that, but each operation is then going to require analyzing the block. They really pulled out the stops on this problem. For each update operation, Farmer John will carve out the 1 by 1 by 1 block of cheese from the integer coordinate xyz to x plus 1, y plus 1, z plus 1. It's a 1 by 1 block at the corner at xyz, where 0 is less than or equal to xyz, extending from the integer coordinate x, y, and z. It's a little bit hard to visualize, but basically what they're saying is if x, y, and z are 0, 0, 0, he's going to carve out the 1 by 1 block at 0, 0, 0 only. The x dimension goes in this direction. This is x. Y is your vertical, and this is z. If I were to cut the block at 0, 1, 0, I would be moving up here and cutting this block in this location right here, which is strictly less than n. They're not going to try and give you the top corner here. All of the cuts they give you will be within the range of the block of cheese. We're not going to have anything that goes out of bounds. It is guaranteed that there will exist a 1 by 1 by 1 block of cheese at the location Farmer John carves, which means we don't have to check to see if he's already carved that location. Every time we get a cut, we can trust that that will remove cheese. This is also a very important information. I'm going to underline it. It is guaranteed that there will exist a 1 by 1 block of cheese at the location Farmer John carves, so we don't have to maintain a collection of previous carves that have occurred. There's actually a much simpler solution. Since Farmer John is playing Moocraft, gravity does not cause parts of the cheese to fall if the cheese below is carved. Moocraft. I actually fired up Minecraft on my desktop to help me visualize this problem. I found it a lot easier to actually build a block of cheese and then cut parts out of it. I found that really helpful. And we're gonna play Minecraft here in a minute. After each update, output the number of distinct configurations that Farmer John can stick a 1 by 1 by n brick in the cheese block such that no part of the brick overlaps with any remaining cheese. Now, this is a very important component to this. If we cut out, for example, a middle block of cheese, somewhere in the middle, we cut out a piece, we don't actually need to search to look for open spaces, because all we need to know is if it's open all the way to the edge on both sides. Because if it's cut all the way through from one side of the block of cheese to the other, that's the only way it can possibly have a length of n. Likewise over here. Unless it tunnels all the way through to the other side, we don't have to worry about it. The only thing we need to do is we need to figure out whether or not we've cut enough cheese in order for a brick to be able to fit all the way through from one side to the other. The world is not always 1,000 by 1,000 by 1,000. The world is constrained to n by n, and we're trying to fit bricks with length n into a spot, which means the only way we can do it is if every single piece of cheese on some particular plane has been carved out. And this is going to be really easy to reduce later on. Every vertex of the brick must have integer coordinates in the range 0 to n, which means we can't do it diagonally or anything like that for all three axes. FJ may rotate the brick however he wants. If you imagine that we've already cut out all of the blocks leading to the top and the bottom and the left and the right, and the last block to be cut out is this one in the middle. Once you cut that one off, that can only add 3 blocks, 1, 2, and 3. However, it should also be noted that if there are a couple blocks, for example, if this middle block is still here and also this one is still here next to it, then cutting out that middle block will open up the vertical direction and the front to back direction, but the horizontal direction doesn't open up until that last block is cut. Input format. The first line contains N and Q. 2, that's N. 5 is Q. The N is the size of the world, and the Q is how many updates are going to be made. The following Q lines contain X, Y, and Z. These are all X, Y, and Z coordinates of the coordinates that should be carved. The output format is after each update operation, we need to keep a running count, not just a final count, of the number of configurations. Now, I said earlier this kind of felt like a silver problem, and it kind of does. There's a lot going on with this problem. We're going to try and pick this apart. We're going to do Minecraft as well, because I used that to visualize, and I personally found that very helpful. We've got this world that's 2 by 2. Initially, we're going to cut out block 0, 0, 0. I'm going to color that blue. Then we're going to cut out 1, 1, 1, which is the block in the top corner. And after the first 2 cuts, you can see it's still 0, 0. The third cut, and this is X, Y, Z. Third cut is 0, 1, 0. 0x, 1y, 0z is this block right here. When we cut that one out, we have room for our first 1 by 1 by 2 brick. And that's where this 1 output is coming from right here. We then cut 1, 0, 0, that's x1 back to here, and then 0, 0, which is going to be this cheese block right here. That allows us now to fit our second 1 by 1 by 2 brick. Now this third one, 1, 1, 0, is going to add 3 more. This is where I had to get into Minecraft because I wasn't able to do this in my head. I'm going to color that one more color. So which blocks are going to be added? We're going to have a vertical block here. We're going to have the horizontal block using the front face. And we're going to have the right to left block on the back face using this. And that's your 3 additional blocks. When we get to a larger world, in order for it to count, the tunnel has to pass all the way through from one side to the other. All right, let's go play some Minecraft. Okay, I haven't played this in a while. Ooh, what is this? We're going to try to figure out how to gather enough to build a cheese block. People ask me what I do for work. I'm just like, oh yeah, I do technical stuff, you know, on the computer. It's all very complicated, scientific. There's like algorithms. You wouldn't find it interesting. Do wolves attack me? I forget how this works. Hey, buddy. You want some mutton? How do I give you mutton? Oh, I guess that's not it. Ah! I'm on the demo version. I thought I had the full version. I have the full version on the iPad. That doesn't make for very good recordings. How do I give? Oh, there we go.
5 hours later.
All right, we're just gonna build a little cheese block. I'm gonna kind of do 2 by 2 to start with. There's a way to, oh, there we go. Okay, right, it's humiliating. Okay, I'm gonna make a marker that indicates 0, 0 with the white wool. Black to indicate the x-axis. 0, 0, 0 is this block. Gonna be this corner right here. X1 is gonna be here. Y1 is going to be here, and then Z is going to work its way across. So Y is up and down, and then Z. I'm in the middle of watching Dr. Stone. Highly recommended. So this is the first block that we destroy. This is the one at 0, 0, 0. That's this guy right here. Second one is 1, 1, 1. Oh, shift to crouch. That's awkward. So it's going to be this block back here. Still no place for a 1 by 1 by 2. X0, Y1, Z0. That's going to be this one right here. Boop, boop, boop. And then that's our first place for a brick. Let's grab some wood for a brick. I'm too lazy to build a crafting table. This is the part where your parents walk in and like, I thought you were studying. I just know that a creeper's going to come and mess this up for me. I'm like under constant trauma anxiety from creepers. Ah! So this is our first 1 by 1 by 2 block. We're just going to place it like this. Boop. Boop, and then no more room yet, so that puts us at one of them. Next one is 1 by 0 by 0, so x1 going that way, 0, 0, that's this one right here. Whoops, bear with me, I'm incompetent. And then 0, 0 just means it's on the bottom on the left, and then that opens up space for my second 1 by 2 block, which is going to go right here. Boop. So that's one of them here and one of them here, totaling 2. And then the final space that opens up is x1, y1, and then z0 is going to be this one right here. All right, and that's supposed to add 3. We got 1 going down to up and 1 going right to left, and then also the one that fits here. That's a third one right there. So I got 2 vertical ones, 2 horizontals, and then this one around the back. Ah! I guess if this USACO thing doesn't catch on, I can always try to be a, oh man, So when does he have so much health? Oh, I don't have a sword yet. Yay. Is there a run button? I swear there's a way to run in this game. Oh yeah, control. Get this cleared up. Ah! Old man still got some moves, huh? Oh. How long does night last in this game again? I would have done creative mode, but I didn't want to pay for it. I'm already over budget thanks to that Captain Naj, whatever. Where is that guy anyway? I think my daughter stole that. Why can't I just hold down the attack button? It's so lame. Build a crafting table and a sword and be done with it. There we go. 1, 2, 3, 1, 2, 3. Thought we all agreed years ago control would be crouch. Oh hey, it's sunrise. So end blocks do fall, by the way. So my x-axis going back this way, y-axis is up and down, z-axis is across the front face here. So when I remove this, if I were to think about this just from a two-dimensional problem, any given row and column combination, in order to fit a block, would have to have all three removed in order to have a length of n. I want to go down there, here's something gurgling. Last one here. So if I were to have the z, remember z is this direction here. If I have a z of 0, an x of 1, which would be this column right here, and then y of 2 were to be removed, y of 1 were to be removed, and y of 0 would be removed, then I would have had 3 along that column, and that's room for one single 3-3 block. If I have from z1, and then y2, I'm up on the top here, and then x0 and x2, if I have an x of 1 and z0 and z2, then I've not yet removed enough to have a single core. When I remove this last block, the count along this corridor and the count along this corridor both are going to be 3. See, so that increases this one to 3, and that one to 3, and that adds 2 blocks. And if these were already removed previously, then you can think about it from the standpoint of this has 2 removed, this has 2 removed, and straight down underneath this has 2 removed. And if I remove that, then that adds 3 new possibilities for inserting a brick. All right, I've had about enough of this. It's been fun. I'll head back over and draw this out and kind of show a little bit more how the matrices actually work. I'm tired of dealing with these zombies. I'll come up with some more excuses to play video games at some point. So let's kind of visualize this as if the front face here represents only the dimensions z and y, and we're going to fill it in with how many cheese blocks were removed from each one of those dimensions. So we have 0, 0, 0, 0 initially. We're going to take the side face here, which represents x and y. I'm going to color code this one green. We have initially 0, 0, 0, 0. And then we're going to make this top face, I'll go ahead and do that one in red, represent x and z. X is the part that goes depth, and z is the part that goes across. We're going to have x and z. X-axis is going to be this, because this is like as if this is up off here. And then z going across the bottom. And initially, again, 0, 0, 0, 0. What that represents is how many have been cut from each of those directions. Initially, when the block is whole, we've had no pieces cut. When we cut out that first piece at 0, 0, 0 here, what we actually did was from the XY face, X and Y, we cut one block here, which is one of the 2 that would be needed in order to fit a block horizontally across XY. From the XZ face, let me actually kind of show how these are connected. This is like here, and then this is the front face. When we cut this here, as far as the ZY is concerned, that's one piece cut here. And the one we cut as far as the XZ is concerned, which is the bottom left, is one here. And once we hit 2 cuts on any given plane, that means we can fit all the way through. So our next block was cut from the far back side, the top right, top right rear. For the top face, that was one here. For the front face, that was one here. And for the side face, that's actually one over here, because that's the back side. This represents the back side. And we still have 0, because none of those have gotten up to n yet. Our third cut is where the magic starts happening. 0, 1, 0 was this piece up here. That is one block here, which didn't result in anything yet. One block here, but from the top-down perspective, that is now the second one cut from this core right here. because this has become a 2, that means we can now add +1 to the number of blocks, and that's how this became a 1. Next update was 1, 0, 0. That's this block back here. That's the first one from this face. And you can see, if you think about it in terms of the left face, we've got the bottom right here, we've got the bottom left here, we've got the top right here, and the top left is this one, but the block behind it. So we still only have 1 from each of those on this perspective. From the top perspective, we now have our first block from the rear left, facing top down. That's the first one. But from the front perspective, that is now the second one that's on the bottom left. It's going to be right here. That becomes a 2, which means now we can do our next +1, and that's what brought us up to 2. Let's do our final cut. 1, 1, 0. This is the one that had the most change. So x1, y1, z0 is this block right here. From the left side face, that's the top left, which is this one right here. That put us at 2, so that's a +1. From the top face, that's the top left that just got removed, which puts this one at 2. That's another +1. And finally, from the front face perspective, that's this front face, top left right here, that's this one. That's going to move that up to 2 as well, which is another +1, which is going to be +3 total, which is how we got to 5. What we need to do from the coding standpoint is for every pair, for the XY pair, we use X and Y for row and column. We add 1 to the number of cuts. For the XZ pair, we have another 2D array, and we add to the XZ using X and Z as row and coordinate. And for YZ, again, we have another 2D array. What we're going to need is 3 2D integer arrays, where each integer array is n by n and represents for each of those planes how many cheese blocks have been cut from that particular plane. That's problem number 2, Farmer John's cheese block. Hopefully this was helpful, and I'll see you on the coding section. All right, we're on to the coding section. I'm starting off with cheese block. All right, first thing I'm going to do is just a quick sanity check. Include IOStream, using namespace standard. I don't think I need any other libraries. Turn 0, test case is comment. All right, compiling and running. Okay, first off I have N and Q, and Q, and Q, and Q. Make sure that's working for int I equals 0, I less than Q, I plus plus. Int x, y, z, cin x, y, z, cout x, y, z. All right, let's grab this guy. Ooh, won't let me paste. There we go. Okay, 2 and 5, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0. Okay, great. Looks like we're reading correctly. I'm going to take the cout statements out. So we need the xy plane. XY is going to be 1,000 by 1,000 potentially. XZ is going to be 1,000 by 1,000 as well. And YZ will be 1,000 by 1,000. All right, so we've just hit our first hiccup. Make cheese / cheese. This works okay, but if I put that third array in there so that I have 3 1,000 by 1,000 arrays on my system, that gives me a seg fault. The reason why that's happening is because this is apparently too much memory. 1,000 by 1,000 is going to be a million, and if it's 4 bytes per integer, then I have 12 megabytes, and 12 megabytes is apparently more memory than my computer's going to let me have by default for the stack, which means this needs to go in heap memory, which is kind of a headache, but it's not the end of the world. So we're going to do that is we're going to initialize these as double pointers, and then we're going to, so xy is new int star with a size 1,000. We can, since we're doing dynamic memory, we'll curtail that to n. xz is new int star with a size of n, and then yz is new int pointer with a size of n. Now for each of those, I equals 0, I less than n, I plus plus. xy at I is going to be a new integer array with a size of n. xz is going to be at I is going to be new int with the size of n, and then yz at I is going to be new int size n. And then I think we're going to have to initialize that since that's heap memory. Int j equals 0 equals 0. Well, j is less than nj plus plus. xz or xy at j equals 0. xz j equals 0. yz at j equals 0. Now, I don't think we get punished for memory leaks on these. So rather than taking the time to tear these structures down properly at the end, I'm gonna let a memory leak happen and we'll see if the system doesn't like that. But what we really should do, if we really wanted to be proper here, is we would have, for all of these, I would delete the array, delete array, xy at I, xz at I, yz at I. I'm gonna put this in here just in case I do end up needing it, so don't forget later. But again, I think we won't get penalized for memory leaks, and it does take up a little bit of time. Delete xz, keep doing xz first. Delete xz, delete yz. But again, for right now, I'm gonna leave these commented out. We'll test that at the end and see if that's any slower or faster. Once we have these arrays allocated, we're going to do int I equals 0 while I is less than q, I plus plus, x, y, z, cn, x, y, and z. And I'm just gonna test that out, x, comma, y, comma, z end line. Make that. Okay, waiting for input. That's a good sign. 2, 5, boop, boop, boop. All right, it read it all in and it spit it all out with commas. So what we'll be doing is for xy, we're gonna do xy at xy plus equals 1, and then if xy at xy equals n. This is a little bit slower than doing the plus plus xy, but I want to keep it easy to read. We'll check and see if it makes a big, I don't think it'd make a very big difference anyway, but we'll check that at the end as well. If that's equal to n, then tally plus plus, and then we'll do the same exact thing for the other two variables, xy, xz, 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 xz. Finally, there's probably a find and replace solution for this, but I'm too lazy to do it. Y, Z, probably just be faster to retype the whole thing, frankly. Y, Z. Okay, and then finally we'll do cout, tally, and line. We're gonna make this, grab our input here. Cursor's weird when I'm doing screen recording. All right, oh, I gotta take that extra output out, but it looks like we got the right answer. I can see the 00125 in there. Make cheese, dot slash cheese, input one more time, and 00125. Let's see how our timing works out on these guys. We're gonna go for C++, '17, choose file, cheese.cpp. Okay, so it looks like our slowest test case was around 400 ms. Just for the sake of comparison, I'm gonna go ahead and do that plus plus xy thing I was talking about. Plus plus. I'm not gonna stress up too much about trying to optimize these though. Again, I wanna keep these solutions simple. C++ 17, choose file, submit. See if that makes a huge difference. Yeah, it's actually even slower, to be honest. It might be a coincidence, but it basically looks like that doesn't make us any faster at all than the plus equals. So we'll just keep that as plus equals. I do want to check and see if I declare these as 1,000 by 1,000, 1,000 by 1,000. See, my system thought this was a seg fault, but we may have more memory on the stack for USACO. So let's clear all that. And I'm just gonna work on the assumption that I don't need to do memset. We'll see if that works. And if not, I'll throw that in and clear it out. Cheese, submit. Ooh. Not only is it slower, I got 2 wrong. That's interesting. That's probably the memset situation. Okay, so we need memset, xy 0, size of xy. xz, yz. Technically, I don't need to change the size because they're all the same size. See if the memset fixes it. That would prove that we do need to, in fact, initialize it all to zeros. Memset's a really fast way to initialize as long as it's stack memory. Okay. Okay. I'm feeling pretty good about that. I think we'll call that one done. So just to clean up this didn't work on my system, but honestly, it didn't hurt us either. So I'm gonna go ahead and set it back the way it was with the double pointer. I know that we're not a huge fan of double pointers, but then it'll work on my system later when I go to test it. We'll run it one more time. With all the, oh, and let's put in the, since we're being prim and proper, we'll go ahead and clean up after ourselves this time and see if this hurts our time at all. And again, I don't think any of this stuff will make any difference as far as the run time. We'll see. Nice not to leave memory leaks all over the USACO servers. Okay, and it looks like it's more or less about the same. So, just to kind of recap, what we did first is read an N and Q. We set up our 1000 by 1000 or whatever N sizes arrays. We set up our tally variable. We go through all our modifications and read it in. So with the XY plane, which would have been on the side, our side view going through, we count in the coordinate of XY as one block removed. It's weird, it's mirrored, it's thrown me off. For the XZ plane, which would have been your top, it's mirrored, so it's confusing. That's one removed. And finally for YZ, which is I represented as the front side with your up and down as your Y and your Z as being left to right. Your YZ, that's one removed going through in that direction. Okay, that's the C++. All right, let's do the Java version. Import Java IOScanner. Class cheese, public static void main string args scanner sc equals new scanner system int n and q n equals, I might as well just do this, equals sc next int q equals sc next int. Create our arrays, int bracket xy equals new int 1000 by 1000, int xz equals new int 1000 by 1000, new int 1000 by 1000, just to see if this will compile. Java C cheese.java, util Java cheese. Okay. So we don't have to worry about the stack situation in Java because one of the fundamental design principles of Java is that everything is always on the heap. So we don't even have a way to use stack memory for these arrays. But the nice thing is that, I guess, I don't know if nice thing, but the default is these are all going to initialize to 0, so I don't need to make the extra loops, which is kind of nice. So we have these that are 1000 by 1000. We now just set our for loop, I equals 0, I is less than q, I plus plus, x equals sc next int, y equals sc dot next int, z equals sc next int, xy at xy plus 1, if xy at xy equal n, tally variable, tally equals 0. We're going to go tally plus plus xz at xz, it's oddly hard to type, plus 1, if xz at x equals n, then tally plus plus yz at yz plus 1 if yz at yz equals n, tally plus plus. One thing of note, I'm doing plus equals 1 and the xy plus xy equal n. This could technically be optimized by removing this and doing plus plus like this and plus plus tally. This is something I've known for a long time. You guys can always change to this style later on if you really want to try and optimize. This is going to run a tiny little bit faster. But just for the sake of making the code accessible to beginners, I'm trying to keep the style fairly simple. So having the plus 1 here, because of the use of the brackets, I feel like the plus plus, xy plus plus like that, I feel like that's a little harder for a beginner to read. So I'm trying to kind of keep it easy. So we'll do x, y, and then the square brackets and plus equals 1. I feel like that's pretty straightforward. And then the tally plus plus is just tally. So that's pretty easy to read. But yeah, I know there's more efficient ways to do this. And you guys, when you get to a certain level, you can swap around your style and your coding practices and stuff pretty easily. Then we got to do system out print line tally. I think that should be it. Let me see. Java. Listen, I should test it on my own system first. Java C cheese.java. It's always good practice to just kind of test it. Java cheese.java. I remember to copy over grab the testing code or the test case here. I'll paste that in, and then 00125. That looks good. All right, we'll do Java cheese.java. Submit. Le fromage. If you skipped ahead, the C++ ones on the higher test cases were around 400 milliseconds. These are around 1800 milliseconds, which is about 4 times as long. But, you know, again, we're passing all the cases, and I don't want to get lost too much on min-maxing. I was talking a little bit about the plus XY thing being a little quicker. Let's go ahead and actually see. So on these highest test cases, I got between 1600 to 1800. Let's pick 14 because that was 1800 exactly. That'll be easy to remember. Let me see what happens if I do remove this and do plus plus and really try to min-max this out. Plus plus. Yeah. If plus plus, then plus plus tally. Okay, we're looking at test case 14 being at 1800. I know there's going to be little deviations each time, but we'll just check and see. 1800 on 14. Submit. I mentioned one of the reasons I like C++ is it does get your test cases back a little faster. Yeah, they came up with 1645, so it does seem like that was a little bit quicker. Maybe that is worth doing. You know, again, as long as you can read it, as long as it's comfortable, it's passing either way. These USACO tests aren't really testing your ability to use min-maxing techniques so much as your ability to just write code that's in the right complexity. So, all right, moving on to Python. I don't think I need to include anything. All right, let's see. So we have nq equals map int onto input split strip first strip split, and then for I in range q, I like to do for I, even though I don't need this variable. A lot of times people put an underscore here. Again, just for the sake of making this easy for beginners, I want to kind of keep it simple. You guys can do that min-maxing fancy stuff later on. Oops, let me get my console back up. Clear. All right, for I in range q, we're going to have x, y, z. This is going to be input. Yeah, we'll just grab the same thing here. It's the same code. Input strip slit. Tally starts as 0. We need our planes. XY is going to be, for the initialization, that's going to be a little trickier because XY is going to start off as a list, but we can't just do 0 times n here because that would be a one-dimensional array. So one thing to point out is that if I try to initialize like this, you would think this would work. Cheese.py. Let's just do 3. So it looks like it works, and a lot of people make this mistake. And the reason why this doesn't work is because when I do this times n, I'm actually copying the memory pointer of that inner list 3 times. So if I now do xy 0, 0 equals like 99, and I run that, notice I have 99 in each of these. So I do need to initialize them in a different way than this. One way to do this is with list comprehension. Another way to do it is just with a for loop. Honestly, I'm not a huge fan of the list comprehension solution, just again, because it's not super accessible for beginners. But basically what that would look like is this would be like 0 times n for I in range n. Now, if I do that, you notice it only affects the first one. So this is one way to do it. The other way to do it is just to start this off as an empty list. And then for I in range n, xy append 0 times n. And then again, that'll work. So again, just for the sake of kind of keeping it accessible to beginners, I'm gonna do the XY append version. It's not a huge difference in terms of speed, and it won't affect whether or not you pass the question. It is a little more efficient to use the list comprehension thing, and if you're comfortable with that, go for it. List comprehension is a fantastic tool if you can get used to it, but I don't wanna make it harder than necessary to start with. So we'll just kind of keep it simple. XY, XZ, YZ, and then we'll do XY, XZ, YZ, XYZ. We can't use plus plus on this. We're going to do X, Y at X, Y plus 1. If X, Y at X, Y equals N, tally plus 1. XZ at X, Z plus 1. If XZ, XZ, ooh, that one almost worked out well, N, tally, plus 1. Finally, YZ at YZ plus 1. If YZ at YZ equals N, tally plus 1, print the tally. Okay, so essentially what I'm trying to do here is I initialize my 2D arrays, my 2D lists, I guess in this case. I set my tally to 0, and for every update, I read in X, Y, and Z. I'm gonna have to map int onto all that, so those will all become integers. XY at the location XY is 1, because that's one block missing from XY, which is that side plane on that direction. XZ, which is my top down, is now missing 1 from the XZ coordinate. And then YZ, which is that front, is missing 1 from the middle point. And then print tally, and that should be all there is to that. On 3, cheese.py. And then we'll grab our test case. All right, we'll test it against the sample case. 00125 looks good. Let's go ahead and run it through the system here. Python 3, choose file, cheese.py, and submit. This is actually faster than the Java as well. It's interesting. I would have thought that Python would be a little slower since it's a scripting language, but Java's got that virtual machine, and that does add a lot of time. So you'll notice too, I'll go ahead and just real quick do a comparison on the time it takes to execute. For the slowest one that I had on Python was number 14. It was 1,331 milliseconds. In the Java version, number 14, I believe was also the slowest one. The first pass I got 1,800 on it. And again, I mentioned I like C++ because you get auto-grader responses a little faster. It's a small amount of time, but that 10 seconds feels really tedious. So I got 1669, so not too bad. A little bit slower than Python. But then we go to C++, and we'll go C++. I wonder if there's a difference between 17 and 16. $414 on the worst test case. So it's about 4 times faster. Let's try C++ 11. Oops. I should write this in classic C just for fun. don't think anybody's doing that. Yeah, it doesn't seem to make a difference. Let's throw this into C just for fun. I want to see how fast it runs in C, if C's any quicker. Okay. Thio. I need standard lib for the malloc. There's no standard namespace. Int main, scanf, %d, and q. I think I gotta, do I have to ampersand these? I won't do a ton of C. Q. Those are double pointers. Malloc, size of int star times n. I'm just gonna copy paste that. Y, xz, yz. Same thing again. Malloc, size of int times n. All right, oops. Cheese.c. Tally. If I want to be really formal, I should declare this outside of the loop. Int I equals. If I want to be really formal, I should be declaring this outside of the loop, but it'll be fine. Scanf, %d, 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 x, y, z. I think the rest of that's the same. Printf, %d, \n tally. And then again, I think I gotta send ampersands on those guys. And then free x, y, I. I think it's just free x, z, y, z. And then free xy, free xz, free yz. I don't even think I have a C compiler on here. See if this can just compile C. Make cheese dot, oh. I'm gonna rename that so I don't have a file name conflict. We call this cheese C. Make cheese C. Cheese C. Still works. All right, let's try that out. So 426 on 14 is the time to beat. If this is faster, I might just start doing these in C. Be good practice. 1 millisecond. Oh, good Lord. That's 4 times faster than C++ as well. That's crazy. All right, so maybe start doing these in C as well. Does anybody even do these in C? I'm just gonna leave it. That's kind of fun. I don't think I've ever tried to do one of these in C before. All right, so that's Farmer John's cheese block, and I've wasted a whole lot of time doing that in a language that probably, I wonder how they scale that. That's crazy fast. All right, well, that's Farmer John's cheese block. I hope that was informative for you, and I've got 3 hours and 20 minutes to get the other ones done, so I'm just gonna move right along.